All right, welcome everybody to already the fifth installment of the lectures on functional programming. I want to start today by pointing you at the website, the ICFP 2009 website. There you can find all the talks and invited talks, keynotes and so on from the ICFP 2009 conference that was held this summer. And I can really recommend that. There's a lot of great content there to complement these lectures and where you can see where the kind of research is at the moment. So if you have time beyond watching the lectures, definitely go and have a look. All right, close this window and let's get started with our lecture for today. So today we're going to talk about list comprehensions, and list comprehensions are very dear to my heart because list comprehensions are the basis of LINQ. So if you see LINQ in C# and VB, think of list comprehensions in Haskell. So like many other things, list comprehensions didn't just start in Haskell, they have an even older history. And they come from mathematics. What else? That shouldn't come as a surprise. Every time there's something cool coming up in these lectures, it comes from mathematics. And again, the same here with comprehensions. Comprehensions come from a set theory, where people write sets in a way to kind of give the elements of the sets, describe the elements that are members of a set in a nice way. So in the example here, it gives you the set of all squares for numbers between 1 and 5. So you write, curly open x squared such that x is in the set 1 to 5. So actually there are two set comprehensions in this set comprehension. The inner one that says x in 1 to 5, that's a set comprehension. And then the outer one that says x squared such that x in this other set. Now, of course, sets are computationally not a very convenient data structure. And the reason is that sets require equality. Because sets don't have duplicate elements, you cannot have the same element in a set twice. But that's hard in general, because for functions, for example, equality is not decidable. So while mathematically nice, computationally sets are not very convenient. Another reason is that the order is not important, and with lists instead, they are just ordered from left to right and they can contain duplicates, so that's much better fit with the computations. So in Haskell, if we would write this set comprehension, we use square brackets instead of curly braces. And we don't have like two-dimensional syntax, so we write x, hat squared, such that x is in the list 1 to 5. And here again you see a double use of list comprehensions. There's the list comprehension, the inner one that says, the list of elements between 1 and 5. And then there's the outer comprehension that says, give me all the squares for the numbers between 1 and 5. This expression, x drawn from some list, is called a generator. And the way to look at that is that the expression on the right, so if you write x drawn from 1 to 5, it's this expression that generates values from 1 to 5 and kind of pushes them one by one into the variable x. So that says, how to generate these values. And in LINQ, let's write this expression here. So x squared such that x is in 1 to 5. In LINQ, we would write something like this. From x in, and then observable dot range from 1 to 5. So in C#, there's no special notation for ranges with like the dot dot. So we just use a function for that. and then we write select x times x. So here you see how closely the Haskell notation and the C# notation are related, and that's because both are based on the notion of comprehensions from set theory. You can, of course, like everything that we've seen in Haskell, everything is compositional. So we can take multiple comprehensions and combine them in a single expression. So the next example gives me all the pairs x, y, where x is drawn from the list 1, 2, 3, and y is drawn from the list 4, 5. And obviously this is a toy example, but it is there to show you that the order in which you write these generators matters. So in this case, the first generator goes slowest. So you will see 1, 4, 1, 5, and the inner one, the 4, 5, runs fastest. And then again, let me get my wiper here. That's not a surprise if you're coming, if you're coming from whatever language, because really, let's write this thing now in C#. So let's write from x in range 1, let me see, 1, 2, 3, from y in range 4, 5, select new x, y. So this is the C# comprehension for this example. And as we know, this more or less corresponds to a for each loop, a double for each loop, var x in range 1, 2, for each var y in the range 4, 5, and then yield return new x, y. So here you see that when you write it as a loop, it's obvious that the inner loop runs fastest and then the outer loop runs slowest. And that's what you see in this example as well. And again, obviously, when you change the order of the generators, you change the order of how the elements are generated. So it's easiest to see in the loop. If I change the 2 for each loops, you will see that the elements are generated in a different order. Okay, so let's now go to something that is extremely interesting, and it took me a long time to understand when SQL people talked about correlated subqueries. Correlated subqueries sounds like something very special. It sounds like something you can impress people at a cocktail party. Oh, today I wrote 4 correlated subqueries. It makes you really cool. But really, it's nothing more if you're looking at the list, or at the loops. When you write a loop, that in the inner loop you can use variables that are defined in the outer loop. So here I could use x inside the inner loop, but I can even use that x, of course, here. So I can say, well, generate me all the values from x to 5. And so correlated subqueries are nothing more than queries where in the inner loop you're using the loop variable of an outer loop. So if we write that in this query here in the LINQ form, I can substitute or use x here. And this example does the same. It says, give me all the pairs x and y, where x is drawn from 1 to 3, and y is drawn from x to 3. And then you get the list that is shown in the slide. These correlated subqueries, for that simple, trivial example, are not so interesting. But you can write quite powerful expressions with them. For example, if we want to concatenate 2 lists, let's write down the type. So I want to take I don't want to concatenate a list. I want to take a list of lists, and then I want to create another list. So I want to flatten each of these lists into a single list. And here we see the use of Hungarian notation that spawned some interesting discussions on the website. So from the notation here, we can see that the X's is a list of lists because there's two S's, and again, it's a convention. And now I want to create a single list. So what do? Well, a single list, well, those are elements of type A. Let's call them X. Well, and what can we do? And this is a strategy that we're applying always when we're doing these functional programs. We're just looking at what are the materials that we have here on our plate. Well, we have a list of lists, and we know how to use a generator. Well, when I use a generator, I can say, give me all the lists in this list of lists. Right? And maybe I should have kind of said it explicitly. When you have a generator, on this side, you have something of type list of T. Then on the left-hand side, you have something of type T. So if you're pulling values out of a generator, you're kind of dropping one level of lists. So in this case, I have X's of type list of A, and then I have X's of type list of A. And what I needed is something of type A, because if I get something of type A and a list of them, then I have what I want. Well, easy. We're just applying the generator again. So we're saying, well, if you have a list of things, just draw them all out and return them here. So again, here you see, I've just used the reasoning based on the types, and from that reasoning, just looking at the types and looking what I can do, how I can compose expressions that take one of these types to another type, I can create this function. And really there was no thinking involved. That's what I love about pure functional programming. I don't have to think. I just look at the types and they guide me through what my function should do. Here's another example of list comprehension that uses a guard. And this says, give me all the values between 1 and 10 that are even. This is something that we know from LINQ as well. And let's write this example in LINQ, where we would say from X in range 1 to 10. And instead of saying this predicate just by itself, in LINQ we write where even X, select X. So also in LINQ you can put a guard inside a comprehension, and this will take all the values from this range and will drop all the ones for which this predicate does not hold. So in the example here, you start with the list 1, 2, 3, 4, 5 up to 10. You drop out all the ones that are not even, and you end up with the list of even numbers between 2 and 10. Let's go and look at a couple of more complicated list comprehensions. We have to say here that a lot of the examples that we show are kind of toy examples. Factorial, prime numbers, Fibonacci numbers, that's all on purpose. We really want to show you the essence of functional programming and not trying to dilute that, hide that in kind of complicated programs. We just want to show you really, really simple programs to show what is beautiful about functional programming. And then you can go off and apply this to real complicated programs. But if I would show here complicated programs, that would just blow it away and you wouldn't see what the beauty is underneath everything. So let's look at another contrived example. And this is factors. So what I want to do is I want to take a number and break it down into its factors. For example, the factors of 15 are all the numbers by which that are divisible by 15, or no, I should say, all the numbers it's better to look at the code than to try to explain it as usual. All right, so you look here, you say give me x. I want to find all the divisors of the factors of x. So give me all the numbers between 1 and n such that n modulo x equals 0. Okay, so the factors of n are all the numbers between 1 and n such that n modulo that number equals 0. And that was what I was trying to explain in words. But of course, the list comprehension is much, much more clear than what I can try to say here in a natural language. So now when is a number a prime number? Well, a number is a prime number when it can only be divided by itself and 1. For example, 15 is not a prime number because, you know, I can divide it by 3 and 5. But 7 I can only divide without a remainder when I divide it by 1 or by itself. So we can now define a simple test when something is prime number when its factors are exactly 1 and n. And here I'm using a list for the factors. So I say the factors are 1 and n, which means that I have to be careful when I compute the factors to apply this test, that I compute the factors in the same order. So I'm not doing a set equality here, I'm doing a list equality. So if I would compute the factors in the opposite order, this test would fail because I'm doing a list equality and not a set equality. So that's one of the disadvantages when I move from sets, as I would do in mathematics, to lists that I use in programming. So now we can define what is a prime number. Well, we already said that, what is a prime number. Now I can define all the prime numbers up to a certain value by just generating that list and then filtering out all the prime numbers. So this is a really, really brute force way of generating prime numbers. I'm just taking a list and going one by one, filtering out all the ones that are not prime. And if you're using a more sophisticated way to generating prime numbers, you're not kind of starting from fresh all over. You're using a sieve or something like that to do that more efficiently. But this is a kind of a nice way to show the power of list comprehensions. But this is not a way to really generate prime numbers. Okay, next function, zip. Zip is this very special function that you need to learn to appreciate. It's an acquired taste. And that's one of the reasons that zip was not included in Visual Basic 9 and C# Trio, but it's now in Visual Studio 2010. It will have a zip function. And the reason is that zip is kind of, a little bit unusual because it takes two lists. A lot of the functions that you see in LINQ here take one list. So for example, filter here takes a list and returns a new list given a predicate. So like many is slightly different in that it takes a list and a function and it creates a new list. But still the input is always one list. So you start with one list and from that you filter or you transform or do things, but you don't start with two lists. And zip is different because zip takes two lists and combines them in one list. So the type of zip here says everything. The type of zip says I take a list of A's and a list of B's and I return a list of pairs of A's and B's. And I think I said this in maybe the first lecture or the second lecture. A nicer type for zip would be if you wouldn't use currying, because then it's very clear what zip does. It takes a pair of lists into a list of pairs. And that's a beautiful thing. It like transposes a pair of lists into a list of pairs. And on the slide you see an example. If I take the list ABC and the list 1, 2, 3, 4, I turn that into a list of pairs that pairs up the values of the list at each position. So you get first A1, B2, C3, and then the first list is exhausted, and then zip terminates. So looking at the type signature, when you take two lists and you zip them to create a list of pairs, this list, the resulting list, terminates whenever the first input list here terminates. So that is the behavior of that list when these lists are not the same length. Let's look at a couple of examples using zip. I can create a list of pairs of duplicates of values. Sorry, that's not what we're doing here. Let me repeat again. What do I want to do? I want to take a list, 1, 2, 3, 4, 5, and now I want to create pairs that are kind of the adjacent elements of the list. It's like, you know, like the chain of elements. So I want to create 1, 2, the pair, then the pair 2, 3, then the pair 4, 5, 3, 4, and the pair 4, 5. If you've seen the Channel 9 videos on the reactive framework, you might remember that we use this trick to do drag and drop, where we take a sequence of mouse moves and we want to turn that sequence of mouse moves in a sequence of mouse deltas, because we want to compute, if these are mouse moves, we want to compute the delta between each subsequent mouse moves. And we use exactly this trick there. And in that video I was explained, for a functional programmer that's obvious. So how do you do that? Well, in order to create the list of these pairs, you take the list, you drop the first element of the list. So now I have that list. Let me just write it down here. I have 1, 2, 3, 4, 5. I drop the first element, then I get the list 2, 3, 4. Right, so, and then just write it how that came. So I drop the first element, and now I just zip the list, and what I get is a list of each adjacent element defined as pairs. So it looks like a very, very simple function here, but you see that this has its uses in things like drag and drop. Here's another interesting one where we are using this function instead of drag and drop. Suppose I want to check if this list is sorted. Well, when is a list sorted? When each adjacent element is sorted, right? A whole list is sorted. If I look at each element, each pair of elements, each of them must be sorted itself. So that's kind of, you know, a very nice way of defining what it means to be sorted. And I can easily define it as follows. Give me a list x's, create all the pairs, so draw x, y from the list of pairs, and check whether x is less than or equal than y. So that's a really, really easy way to check whether a list is sorted. It's like a specification of what sorted means. Another use of zip is to find the positions of a list. In Haskell and in enumerable, there is no position associated with an element. So if I have a list 1, 2, 3, 4, there's no index corresponding to these values. What people often do is they say, I want to zip a list, say this is x's, and now I zip that with the infinite list 0, ... This is another list comprehension that gives me the infinite list of values starting with 0. So if I zip these two, what do I get? Well, I get the 0th element of x's paired with 0, the first element of x's paired with 1, etc. So I zip a list with a list of indices, and now I get a list of pairs. And then the example that you show here just drops the list and it gives you the positions. Now what's interesting about this is that in LINQ there's a couple of operators that kind of specialize the use of zip with an index. And these are not very discoverable maybe, and I'm not sure if people use them, but there's an overload of where that has the following signature. Takes where, takes an IEnumerable of t source, and the normal where takes a func from t to bool. Okay, so this says for each element in this stream apply the predicate p. But this doesn't tell you what the index is of the element in the source. Maybe I want to kind of drop out all the elements that have an even index. So for that reason there's an overload here that takes an int and a t and returns a bool. And what that does, it passes to the function here, instead of the element, also its index. So now let's see how we can define this function in Haskell using zip or in C#. So we want to define this function here that takes an extra index in terms of zip and the original where. And it's quite easy actually. So let's define that. Where of x's, and let's call that guy p, and I'm going to do it in Haskell. So I say where of x's and p is zip of x's with 0 to infinity. This gives me a list of pairs, and now I have a predicate which takes an int and a t and a bool. So I need to filter that. So in Haskell that's called filter. And I just pass it p here. So nothing special. I'm just doing a filter and I prepare the list that I kind of zipping with by just generating the index with it. That's a very nice way of kind of hiding the use of zip in that function. This is another nice analogy between Haskell and C#. In Haskell, a string is nothing more, nothing less than a list of characters. So if you write the string ABC, which has type string, you're really writing that string is a list of characters. String is defined as an alias for a list of characters. Similarly, in C#, when you write the string ABC, that implements IEnumerable of character. C# is slightly different. In C# there's this type string that implements the IEnumerable of character interface. In Haskell, strings are defined as lists of characters. But the effect is the same. The effect is the same, namely that I can apply all the operators on list on strings. And the same holds for C#. I can write queries like this. From C in hello, where some predicate on C, select C to upper or something like that. And this guy has now type char, where this thing has type string. And being able to use strings as sequences of characters is extremely handy, because all the operations on list are applicable to operations on strings. Here's another example. give me all the lowercase characters in a string and the number of them. So how do you do that? You just say, give me all the characters in the string, filter out all the ones that are lowercase, and then take the length. So if we apply this to the string Haskell, let's count here. Well, the first one is uppercase, so the other 6 are lowercase. So if I apply lowers to the string Haskell, we get the number 6. And you can write that easily in C# yourself. So this was the end of the lecture. As usual, some homework. We have seen like pairs with zip, but you can make easily kind of triples or 5 tuples or n tuples. So the first exercise here says, given an integer, return the list of triples for which x squared plus y squared equals z squared. And if you look at the English description here, that's already extremely very close to the actual implementation. And then there's a couple of other examples. I won't explain them here. I'll leave that to you to look at the slides and solve the exercises. Again, please, I already closed down the window. Please look at the videos, the ICFP videos. Very interesting content. Do your homework and be active on the Channel 9 forums. And see you next time for Lecture 6. Thank you very much.